Swayam Prabha. Digital India. Educated India.
We are going to start another new phase transformations in the solid state, that is known as eutectoid transformation. As you know, eutectoid transformation is a major class of phase transformation we observe in different materials, and the transformation can be written as like this. Normally we write that a phase which is a high temperature known as the gamma phase undergoes a transformation and forms two phases simultaneously. Here all these phases are actually solid, remember, that is why it is called eutectoid transformation. Now this has a similarity with the eutectic reaction which I have discussed in solidification. We know the eutectic reaction is given by liquid going to two solid phases alpha plus beta. So therefore by simply replacing liquid with solid phase gamma, we could see that the phase transformation eutectoid can be achieved. So this is the eutectic, and whenever we have a tick word in the transformation, must involve a liquid phase, but whenever we have a toid attached to a word, it always involves solid state phase transformation. So this is the classic reaction which you must remember, which is basically giving the idea of eutectoid transformations. Remember, the eutectoid transformation is very important in steels. So most of our discussions in this will be taking example from the steels and explain you how the transformation happens. The steels which actually has a composition from about 0.1 to basically 0.1 to let us say 1% shows the products known as perlite, and which is well known to all the metallurgical community or material science. This perlite actually is nothing but a combination of the two phases forms because of the transformation of the high temperature phase gamma. So that is the important aspect which you should remember. Now as I told you that one of these important corollary of the eutectoid reaction is the microstructure of the steel. So we will start with the iron carbon phase diagram. You know, steels are basically iron carbon alloys, and predominantly it contains iron, little bit of carbon. It can be as low as 0.1 or less than even that, or as high as about 1% carbon. So this is the iron carbon phase diagram shown on this figure. You see here that this y axis is basically temperature in degrees Celsius and x axis is weight percent of carbon. This diagram is well known to you, or it should be well known to you. If not, please go back to my own lecture on phase diagrams in material science engineering. You will find a detailed discussion on these phase diagrams. So as we are going to discuss about the paralytic transformations, especially the eutectoid transformation in the steel, we are not going to discuss the whole phase diagram. Only we will be concentrating on the salient portions which are required for our discussions. What you see here is basically equilibrium between two phases, alpha iron, which is nothing but a solid solutions of the carbon in BCC iron, and another phase which is known as Fe3C, it is popularly known as cementite, and this is basically a carbide. And you see here the gamma, which is basically another solutions of carbon in FCC iron, undergoes a transformation here at this temperature, undergoes transformations. The transformation actually can be easily shown. This transformation what I am discussing at about 727 degrees Celsius temperature, in which the gamma is undergoing a transformations to alpha plus Fe3C. This is also similar to the reaction which I wrote, gamma going to alpha plus beta. So alpha is alpha here, and alpha is basically alpha iron, and Fe3C is beta. So therefore this transformation which is happening here is important in all the steels, because as you see steel has a composition between 0 and 1 atom percentage. That is why in all the metallurgy of steels basically physical metallurgy of steel basically revolves around understanding these reactions. That is what we will see. As you know, as one phase gamma, which is present at high temperature, undergoes a transformation leading to formation of two phases. So therefore the microstructure is very simple here. It will be like a lamellar one which you have seen for the eutectic. Okay. Let me just explain to you first the microstructure and come back. This is a typical optical micrograph of a perlite which you normally see in the plain carbon steel. As you see here, it consists of two phases, one which is white continuous, other one is like a plate. So and these are actually plates having different orientations in the microstructure. So normally these plates are actually known as Fe3C, they are the carbides, and whether this continuous phase is known as alpha. So therefore the microstructure basically consisting of transformed gamma into two phases Fe3C plus alpha. If we want to know a little bit about it, let us go back. By the way, cementite has a very complex structure. It has orthorhombic crystal structure, and you see these are the carbon atoms, okay, and shown here. So these are the carbon atom inside, and these are the blue color atoms, actually iron atoms present on the lattice. They actually forms like a tetrahedral coordination between these atoms, sorry, octahedral coordination between these atoms. There is a octahedra inside each of these. These are the octahedron atom, octahedron corners on which the iron atoms are sitting, and inside that there is octahedron center on which the carbon atom is sitting. And these octahedra actually are attached each other along the corners. That is what you see here. These corners actually attaching the octahedra. That is how this orthorhombic complex structure forms. So basically carbon atom goes to the octahedral voids in the BCC iron lattice. So that is how actually it forms, distort the lattice and leads to formation of orthorhombic structure. Okay, now as you know, iron is a classic metal which undergoes polymorphic transformations, as I discussed in few lectures back, that iron actually is a BCC structure at room temperature which is known as alpha iron. At about 912 degrees Celsius temperature, it undergoes to gamma iron and becomes FCC structure. Again at a high temperature at about 1492 is again it's become delta, and then finally at 1539 degrees Celsius temperature this melts down to liquid. So therefore the important transformation for our discussion is basically between gamma and alpha, and this is for the pure iron when there is no carbon. The moment we add carbon into it, things gets changed. That is what is shown in this phase diagram. As you add carbon into it, as you see here, the transformation which was happening for the alpha to gamma at 912 degrees Celsius temperature, it decreases. That is what is shown by this line. This line which is this curve which is showing is telling you that transformation temperature of gamma to alpha basically, or alpha to gamma, is a strong function of the carbon concentration in the alloy. So this decreases very rapidly to about 0.77 weight percent of the carbon, and where there is a dip or there is basically a lowest minimum position, and at this temperature there is a horizontal line as you see here. This horizontal line corresponds to a reaction, and that reaction is basically eutectoid reaction which you have discussed few minutes back. Okay, and at a higher concentration of carbon again this transformation temperature increases, it goes higher when the alpha to gamma transformation has to happen. Okay, so therefore and at high temperatures again several other phases forms which are not our concern. So important thing to remember is that this transformation temperatures which is 912 for the pure alpha pure iron and at 727 degrees Celsius temperature for the eutectoid reactions. Okay, let us now discuss how this transformation actually happens. Obviously any transformation will happen by nucleation and growth, correct. So this is the typical microstructure. If you look at in an electron microscope, this will look like plates. As you see here, the black thing is basically Fe3C and the white color thing is basically white contrast thing is basically alpha phase. And this has a nice plate like microstructure, alternative arrangements of these phases present in the microstructure. Similarly, here also you can see even the plates are there. Some of their cases are this as the broken plates, but this is alpha, this is cementite present. As you clearly see, if you do the phase diagram calculations properly, then normally the fraction or the volume fraction of the phases at about eutectoid temperature for the 0.77 weight % carbon alloy will be 85% of alpha, and remaining about 14 to 15% is Fe3C. Now, if we know the densities of these alloys, both of the phases alpha and the Fe3C, you can clearly see the ratio of the thickness of the cementite and alpha will be 7:1. That is possible to calculate. In fact, this will be one of the problems in your assignments, to calculate this thickness of these phases in the microstructure. Okay, so let me just explain you how the things forms, how the actually transformation happens. Let me just go and okay. Obviously, this is the classic microstructure which is normally shown in the books. This is taken from from the book by Darken and Fisher in decomposition of austenite by diffusional processes. This is the interface, this is the gamma, and that interface is between gamma and the reaction product. Between reaction product is obviously alpha and Fe3C, this is Fe3C as you see here. So, what you see here, as the interface moves, both the phases are going together. So, that means this is a cooperative growth. But before that, let me just tell you, in most of the cases nucleation of these phases happens along the gain boundaries of the gamma phase. These are the gamma. So, nucleation is normally happens on the gamma. That is obvious, because the gain boundaries are the regions of gain boundary, gain corners, gain edges, or even triple points are the regions of where the nucleation probability is high. We have seen that in our discussion on nucleation. The same thing will happen here also. So, all the nucleation will start happening from the gain corners or their gain boundaries or maybe edges. That is what is seen here. Then these colonies grows inside the grains. It can also happen within the grains, something like that, if there is a compositional inhomogeneity or some defect structure present, like dislocations or a void or vacancies present like that. It is possible, but preferentially nucleation happens along the gain boundaries or gain edges and gain corners. That is the one important aspects. Now, once the nucleation happens, the nucleation can happen for any of these two phases, either alpha or Fe3C both can nucleate side by sides, or they can nucleate separately. So, mostly it has been seen that for the hypereutectoid alloys, the alloys contain less than about 0.8% carbon, nucleation is normally happens for the alpha phase. On the other hand, for these hypereutectoid alloys, it mostly starts with Fe3C. Whatever be the situation, the transformation does not change, transformation process does not change much. Okay, let me just tell you how it happens. Let us assume there are two gains of gamma, gamma 1 and gamma 2 here, and let us assume that the Fe3C is the phase which starts nucleating on the gain boundaries. Let us assume, it can be, you can also assume that alpha nucleates at the gain boundaries. And as you know, Fe3C has a composition of Fe3C has a large amount of the carbon concentration. It has a carbon concentration of 6.67% weight % carbon. On the other hand, alpha has a very low carbon concentration. It is about 0.02% at a 727 degrees Celsius temperature, and room temperature is almost 0. That is what is seen in the phase diagram. So, what will happen, as the Fe3C is a carbon rich compound, it requires more carbon for its growth. So, when it grows into the one of the grains which it has incoherent interface, that is obvious, because the grain with which you have a coherent interface will remain stagnant, because it will like to keep these coherent interfaces or semi-coherent interfaces present. It will not try to disturb. That allows it to have a low energy, and the moment the grain with which has incoherent interface, that will be the one which will be mobile. So, as this Fe3C grows into the gamma 2 grain, it grows requires carbon. So, all the carbon from the nearby region will diffuse into it. That is why it can achieve a sufficient amount of carbon for its growth to happen. And because of carbon diffusion from these nearby regions in the gamma 2 grain, the resist regions will be lean in a carbon concentration, because carbon is growing, carbon is moving actually diffusing into these gamma and reaching these Fe3C nuclei or nucleus to grow. and this will lead to a huge reduction of the carbon concentration in nearby regions, and therefore this allows nucleation of the alpha, because alpha has almost no carbon in required, it has no carbon is there in the phase, because alpha has, as I told you, at 727 degrees Celsius temperature, it is carbon concentration alpha is about 0.02 weight percentage, at room temperature it has no carbon concentration required. So because of that it can grow very easily, nucleate actually on the both sides of the gamma, both sides of Ap3C and grow in the same direction as you see here in this direction, correct. And as growth of alpha requires rejection of carbon, it does not require any carbon, so therefore nearby regions will become rich in carbon, and this will lead to further nucleation of the Fe3C. And this is exactly how this nucleation and growth of these phases happens, and this leads to colony formation. This is a colony, and as we have seen in the microstructure, the colonies forms. Okay, let me just this is one such colony you see here shown on this picture. That's the this is a one colony, and this is a gamma grain. This colony is growing into the gamma grain, and this is normally observed. So therefore I can easily explain the formation of or the growth of these paralytic colonies in the transformations. Now you can also have something like alloys which are not 0.77% carbon. It can be hyper-eutectoid or hyper-eutectoid. If it is hyper-eutectoid, you will have a pro-eutectoid cementite. Okay, we will discuss how it can happen, because the alloys which is more than 0.77 weight % carbon will always have a pro-eutectoid cementite present. And this pro-eutectoid cementite, if it is present on it will present on the Gann boundaries mostly, because Gann boundaries are ones which will allow nucleation of these pro-eutectoid cementites, and if it is present on these, it will lead to easy nucleation of the cementite for the perlite. Okay, that is what is seen here. This cementite which is there can easily nucleate over heat very easily. Okay, and because of that, because it can nucleate over heat very easily, and because of that it can actually have certain kind of structure like that. And again once it goes into the gamma grain, this requires more carbon, so all the carbon will diffuse from the nearby region, and the nearby regions will be lean in carbon concentration, and this will allow you to basically nucleate alpha phase very easily on the both sides of these gamma, both sides of the cementite, and this will again lead to formation of colonies. So therefore nucleation of these phases can happen in many ways. Similarly, for a hyper-eutectoid alloys, you will have alpha on the Gann boundaries, like if I have two grains gamma 1, gamma 2, and then you have alpha presence, which is pro-eutectoid alpha, and this alpha will again allow the nucleation of the alpha phase of the perlite very easily, because it is heterogeneous nucleation, and heterogeneous nucleation on the same phase. So therefore energetically this is very favorable. And because the growth of alpha requires less amount of carbon or actually no carbon, so what will happen? The nearby regions will become very rich in carbon, and when the carbon concentration reach the critical concentration required for the nucleation of these Ap3C will nucleate on the both sides, and finally it will lead to a formation of a colony, and this colony will have this phase which is pro-eutectoid alpha as a nucleating site, not the gamma Gann boundary, but pro-eutectoid alpha, and this will be followed by formation of these colonies. Okay, and these colonies will be again looking like same like a perlite. So as you see, nucleation is not a very critical step for the formation of perlites. That is very clear. Nucleation can happen many ways. It can happen on the pre-existing Gann boundaries of gamma, or it can happen in the pre-existing pro-eutectoid phases, either cementite pro-eutectoid or pro-eutectoid alpha, and this can lead to formation of these colonies. So therefore either way, whatever be the situation, it will lead to formation of these colonies which you have seen in the microstructure. Okay, like that. So that is how actually the most of the phase the important transformation of paralytic phases happens. Paralytic phases means the phases of gamma plus alpha plus cementite actually takes place in these steels. Please remember that this looks like a very simple, but when you analyze kinetically it is not so. There are many important aspects which you need to deal with. The first one is how actually the nucleation rate and growth rate will depend on. What are the different aspects? Obviously, the important thing to consider here is the diffusion of carbon. Whether it is a growth of alpha or growth of cementite, in both cases you require either carbon to be diffusing out or carbon to be diffusing in. In case of alpha, it requires carbon to be diffusing out from the alpha to the gamma, and in case of growth of cementite, it requires carbon to be diffusing in from the gamma to the cementite. So, it is basically diffusion of carbon which is more important. That is very clear. Second important aspect, obviously the interface energies between these, between the gamma, alpha and cementite. So, these other than that, there are other things like amount of driving force available which is connected to the undercooling, and obviously the nature of interfaces created. This will all be playing an important role in dictating the nucleation and the growth rates. So, in the next lecture which we will discuss in these aspects in a detailed manner.